Hello. So today is going to be chapter 5 lecture or the chapter 5 lecture. And we're going to go do things a little differently today. The majority of this is about Newton's three laws of motion. So I'm just going to go over those really quickly, 15 to 20 minutes probably, and then do a bunch of problems. But in those problems, there are also going to be a few extra theoretical values. So you should probably watch that if you want to understand the chapter completely, or you can also find them in the book. So first off, we have Newton's first law of motion, which is simply enough. I'm going to look it up in the book so I get the language completely right between this. A body A body at rest remains at rest, or if in motion, remains in motion at constant velocity unless acted on by an outside force, on by a net external force. So what this means, so what this means is that in the more traditional way that we would put this, an object in motion since to stay in motion unless acted upon by an outside force, uh, is that any object that is going forward or is staying still will continue to act in that same direction, in that same velocity, unless acted upon by the outside force. So the ideal that you need to apply a force to move something is kind of intuitive, but the ideal that you need an outside force to change the velocity of a moving object is less intuitive because back in the Greek times, back in well before Newton appeared, I think it was Aristotle who believed that an object in motion would automatically go to stop or it would automatically stop or go to a lowest point because different objects have different properties, which means that they are going to go to their natural state of being, which for massful object, I think, was just stopping at the lowest point possible, trying to get as close to the Earth as possible. While now we know that unless there is a force acting on it, such as force of friction, then it's not going to stop. So if you talk about an object just moving across a rough plane, so if you talk about an object just going across a rough surface, then the force of friction is going to pull back on the object and stop it moving. But if you make that force or if you make that surface smooth and with no friction, then it will just keep moving forever and ever with no uh, interference or no external force being acted on it. So what another form of this equation is that uh, there are inertial reference frames, which is a frame, which is when you're looking at something also moving at a constant velocity. there is no more privileged frame than any other frame. So if you're talking about movement along a train or along the station, then there is no more natural way. Uh, it is not more natural for the movement to be along the train and or along the station, and the movement of the object will not try to uh, come to the station. It will not try to revert to the motion in respect to the station, but will stay motion, uh, stay as motion in respect to the train. So in respect to what is moving uh, relative to a relatively stationary or what we can call a stationary frame. So basically any moving frame, any moving, when we look at any system that's moving, uh, it is no less privileged than a system that seems to be standing still. But if you look at it from another point of view, the train could be standing still and the station could be moving backwards, and that's a perfectly valid way to look at it. So we write out inertial reference frames. A reference frame moving at a constant velocity relative to an inertial frame is also inertial. A reference frame accelerating relative to an inertial frame is not inertial. So what I was saying about there being no privileged reference frames does not count if the frame is accelerating. So if a car or a train is accelerating relative to another frame, relative to the station, then you cannot use the same laws of motion as you would with inertial reference frame, so a frame that's just going at a constant speed. So Newton's second law. Newton's second law simply states the way that a force changes a motion. So basically, what they found, or what Newton found, is that acceleration was inversely proportional to the mass of an object. So mass is, we've gone over this a little bit, but mass is kind of like weight, except weight is a force that depends on where you're talking about. So weight is actually a force mg that depends on the gravitational acceleration of the planet or the moon or whatever you're on, while mass is just a property of the material. So something that weighs more at the same place, at the same planet, is going to have more mass. And something with that's made of the same material but is twice as big will have twice as much mass. And something that's denser will have more mass than something that's less dense. So what they found, or what Newton found, was that acceleration was inversely proportional to mass. So let me just put 1 over m here, which means that mass times acceleration can be said to be equal to some force that's moving it. So because acceleration is inversely proportional to mass when you apply some sort of force, then we can define force as being mass times acceleration. So with a constant force applied, A equals F over m. So acceleration is force divided by mass, which means that acceleration with a constant force is inversely dependent on the mass of the object, which is what Newton observed and gives us this equation F equals ma. But of course, F and has to be a vector because A is also a vector. So force equals mass times acceleration, whereas mass is a scalar. So another thing that we need to note here is that instead of being any force that's acting on it, it is only the net force acting on a body that counts as that will cause an acceleration. So F net equals all of the forces added together that are acting on the material or on the object, and F net equals F1 plus F2 plus F3 plus so on and so forth for all of the forces. And if all of the forces cancel out and uh, say you have a force of gravity pulling down, and then you have the normal force, which is something we'll discuss in a little in with Newton's third law, pushing up, then those two forces are going to cancel each other out exactly, which means that there is no acceleration. So you can't just say, oh, gravity's working on this, so it has a acceleration of 9.8 meters per second squared. You have to care about all of the different forces that are acting on it and add them up in order to find the net acceleration. So equals, so A would equal 0 in this case. Now for Newton's third law, this is again less of an, no, this is an equation, but it is also given, I think, in, oh, uh, actually, one more thing about Newton's second law is that instead of being equal to dp or dmda, or sorry, that was just obnoxious. So instead of just saying it's equal to ma, you can say it is equal to the change in momentum over change in time, where momentum is defined as m times the velocity. Yeah, that's unnecessary. You know what mass is. So dp dt equals d dt mv, which if we're just talking about an object and not, say, a rocket ship, which moves by ejecting all of its mass, uh, then the object is going to have a constant mass. So m dv dt equals m a. So this is another proof that F equals dp dt, because dp dt is also equal to ma. But in coming weeks, we're going to be using the definition of momentum in order to do calculations that don't require us to worry about force. So this is a convenient thing to bring up now. So let's actually move on this time to Newton's third law, which is whenever one body exerts a force on a second body, the first body experiences a force that is equal in magnitude and opposite in direction to the force that it exerts, which in mathematical terms means that force of B on A is always equal to negative force A on B, which basically just means that when you're talking about uh, hitting something or like applying to a force to something, the force is going to apply a force back, or the something that you're applying a force to is going to apply a force back onto you. So when you hit a tree, the tree hits you back. When you hit uh, another car, that car is also going to crumple your car. When you're pulled down by gravity and hit an object, hit the floor, then the floor is going to push back on you and cause you to experience a force pushing you up. So this is also related to the definition of normal force, which is the force that is exerted when you are in contact with another object. And that is what it's called when you place a book or place yourself onto a table and are held up by the table, even uh, the table exerting a force on you, even though the table is also experiencing its own gravity, which is pulling it down, it is exerting a force upwards onto you. So that's what's called normal force. And then while we're at it, we can also define contact forces when a force is when two materials or two objects touch each other and exert forces that way, which is like normal force, like uh, picking up a glass or brushing your hair or anything that involves contact and choosing and being moved by something that you are directly touching, and field forces, which are forces that uh, exert themselves over space despite the objects not touching. For example, gravity, electromagnetism, and the strong and weak nuclear forces. So when we're out in space, we don't actually touch the surface of the Earth, but this Earth is still pulling us down using gravity. And less than saying e.g., I should say that is to say i.e. Uh, the it's still pulling us down due to gravity, where gravity is pulling or pulling an object even though there's no contact between those objects. And then for our final thing that I'm going to say about Newton's third law, it's that uh, even though even though there is always an equal and opposite reaction, that does not mean that they cancel out in net force, as they are acting on different objects and causing them to, the different objects to accelerate in different directions. So when you have F A on B and negative F B on A, which is equal to negative F B on A, then you have the forces uh, are of equal and opposite magnitude, but one force is acting on object A and one force is acting on object B. So when they collide with each other, or hit each other in any other way, like gravity or the electromagnetic force, then because they're acting on two separate objects, they'll accelerate in different directions, having been acted on by an object or by the other object. So hopefully that's clear. That's why it doesn't automatically cancel out, because these two objects are acting on each other in different directions. So with that said, that's the majority of this week's lecture. That's just how the three laws work with each other. So with that said, I'm going to do some uh, example problems. So for example, let's see. if we have an acceleration equals 3.0 I, or in the I direction, plus 7.00 in the J direction, meters per second squared, and we have a mass of an object being 0.400 kilograms, then the force on the object is equal to m times a, which is equal to 4.0 times 3.00 I plus 7.00 J, kilogram meters per second squared, because that's just the combination of those two units, the meters per second squared and the kilograms, because they're multiplied next to each other, which is the standard SI unit for force. Also called the Newton, in honor of Sir Isaac Newton, who came up with these three laws in. So this is equal to 12.0 0.40. I'm silly. Is equal to 1.20 I plus 2.80 J newtons. So those are our components. In order to find the net force acting on them, the magnitude is taken from 1.20 squared plus 2.80 squared, and then the square root of that is going to give you the uh, magnitude of the vector, which is the same thing that we've been doing with vectors for like 3 weeks now. So hopefully you have a handle on that, which is equal to 3.05 newtons. And then theta equals arctangent of 2.80 over 1.20, which is equal to 66.8 degrees. So this is just showing how to do scalar multiplication of vectors, and also that since force is a vector, it still obeys all of the laws that we were talking about when we were adding unitless vectors. And this is also something that came up briefly on the, or not so briefly on the midterm, or the exam one, where you can add Newton forces together in the same way that you add normal vectors with no units. Okay. Uh, so four forces are applied to to an object. What is the net force on this object? So, uh, magnitude of F1 equals 10.0 newtons. F2 equals 5.0, or F3 equals 5.0 newtons. So F2 is equal to 40.0 newtons. F3 is equal to 5.0 newtons. And F4 is equal to 2.0 newtons. So in order to find F net equals F1 plus F2 plus F3 plus F4, we need to break this up into X and Y components, like the same way that we've been adding vectors up until this point. So F net X equals F1X plus F2X plus F3X plus F4X, and F net Y is the same thing but with Y. F1Y plus F2Y plus F3Y plus F4Y. So F1X is equal to 10.0 cosine 30 degrees, because that is the angle that F1 makes with the x-axis, is equal to 5.92. Oh no. 10.0 cosine 30 is equal to 1 over 10 over the square root of 2, so that's going to be 5 square root of 2. I don't remember what that is. So whatever that is. F2x equals 10.0 cosine of 270 degrees, which is equal to 0. F3x equals 10.0 cosine 180 degrees. Oh no, sorry. I keep adding 10.0 when really I should be adding or multiplying by the correct numbers. Equals negative 5.0. And F4x equals 2.0 cosine 90 degrees equals 0 newtons. And then do the same thing for Fy equals 10.0. Oh, 3 square root of 2. So this is actually 5 square root of 2 over 3. Uh, let me just or yeah, 5 square root of 2 times 3. So instead of trying to solve this in exact numbers, I'm just going to say that 10.0 cosine 30 is 8.66 newtons. And F1y is 10.0 sine 30 degrees, which is going to be equal to 5. Yeah. Oh, yeah. That was a boo-boo. 5 newtons. F1, F2y equals 40.0 cosine 270 degrees, because that's where it is. That's this length, equals negative 40.0 newtons. F3y equals 5.0 sine, oh, yeah, 180 degrees. Not cosine, sine, because we're talking about the y direction, and f4x or f4y equals 2.0 sine. This is equal to 0. And then 2.0 sine 90 degrees is equal to 2.0 newtons. So if we find the net force, then F net x equals 8.66 plus 0 plus negative 5.0 plus 0 equals 3.66 newtons. And F net y, let's just put this on the same line, or in the same column, I suppose, equals 5 plus negative 40 plus 0 plus 2.0 equals negative 35 plus 2.0 equals negative 33 newtons. And then if we want to find the acceleration, if that's something we want to do, for m equals 4.00 or 4.0 kilograms, then ax equals 3.66 divided by 4.0 equals 0.92 meters per second squared, and ay equals negative 33 divided by 4.0, which is equal to negative 8.3 meters per second squared. So F net is equal to 3.66 I plus minus 33 J newtons, and A equals 0.92 I minus 8.3 J meters per second squared. So if there is so let's do a scale in an elevator problem. So what is happening with the scale? Okay. So first I'm going to introduce you to free body diagrams, which have a number of rules for how to create one, which I'm just going to pull up from the textbook right now. So basically, a free body diagram is just a drawing where you try to create uh, try to count up all of the objects on the force on a body. So what we saw earlier in the last diagram was a free body diagram. But if we're talking about weight and normal force, then a free body diagram would just draw the object under consideration. So in this case, I just drew a particle. You can draw a box or a car or something, and include all force acting on the object. So in this case, it would be weight and the normal force pushing back from a table. So this is describing just a book lying on a table. And if we start pulling it with some force we'll call tension, if we attach a string to the book and start pulling across the table like that, then we're also going to get a tension force and a friction force, which are going to be acting in the y or the x direction rather than the y direction. So just draw out all of the forces acting on the bodies, then resolve all of the force vectors into x and y components. So in this case, it's like we did in the previous problem. Fx equals T minus friction, tension minus friction, and Fy equals normal force minus mg, which is also the same as normal force minus weight, which is the convention I think that they use. And then just that's drawing a free body diagram. It's just a way to keep track of your forces and to keep track of how you drew them out or how they react with each other or like add to each other or don't add to each other, whether one's all in x direction or one's all in y direction or so on and so forth. So with that said, uh, we did a free body diagram, and what a scale in an elevator problem is if you are sitting on some scale that reads out the force that's acting on it, then if you're accelerating or decelerating, then there's going to be a different force acting on it. So the way that we set this up is we have two bodies. One is a box, which is sitting on the scale and is being pulled down by weight, and pushed up by normal force, which is what we talked about earlier, is the force that keeps you from falling through the floor. And the scale is being pushed down upon by normal force because it's going to be pushed down upon with the same force that it's pushing up with. And then it's being pushed up by its own normal force from the floor in order to keep it from moving. So what the scale reads what the scale reads is the same as the force, the normal force, as the normal force exerted on the box, right? Because it's a Newton's third law pairing. So the normal force pushing up on the box is equal to the normal force pushing down on the box. So if A equals 0, 0, then F net equals F net Y in the Y direction, because there are no forces acting on the box in the X direction. So F net Y is equal to the normal force minus the weight is equal to normal force minus mg is equal to m times 0. So normal force, what is going to be m times 0, sorry. Normal force, which is going to be what's going to be read, is going to be equal to m times g, the weight of the object uh, on the scale. So what's read by the scale is equal to m times g. But if a does not equal to 0, then F net Y equals m times a equals normal force minus mg. Normal force is equal to m times a plus mg is equal to m times a plus g. So if you're going on if you're accelerating up in a if you're accelerating up in a elevator, n goes up from actual weight, and if accelerating down, n goes down from actual weight. So what the scale reads out, what the normal force is going to be up, higher, or lower than your actual weight, depending on whether or not you're accelerating up or down. Because the normal force that's necessary to accelerate you up is going to be greater than the normal force that's just keeping you in the same position. And there also the normal force that's needed to accelerate you downwards is going to be less than the normal force to just keep you in the same position. Um, yeah, and then when you're running, when you're a little person, like a little stick figure running, then you push on the ground to the down and to the left, or to your towards your backside, and then the ground will push you forward and uh up, which is what we do when we run. We just push down onto the ground and behind us, and then the ground pushes us back. And this is an example of Newton's third law pairs. Let's see, what else do we have to do? Ooh, so let's uh one more problem, and then I'm going to define a few types of forces. So if you're a skier going at some angle, being pulled down by gravity, and being pushed up by the normal force of this ramp on you. So if you're a skier on a ramp, then uh, you're going to be pulled down at an angle uh, so that not all of the gravity is pointing along the direction of the ramp, and not all of the gravity is pointing along the direction of along the direction perpendicular to the ramp. So you're going to have some acceleration that isn't mg. So in order to find this acceleration, I'm going to draw you as a box because that's easier, and say that you are accelerating downward towards the center of the earth while there is some angle theta being made uh with the ground or with the flat surface of the earth. Not that the surface of the earth is flat, but with uh the general surface of the earth when there's no hills nearby. So mg, you're being pulled down, and this uh angle that you're being pulled down with is perpendicular to the angle of the flat surface of the Earth, or the surface of the Earth where there's no hills. So if that's the case, then theta is going to give root to 90 degrees minus theta here, which means that there's theta degrees made with the normal, made with the perpendicular of this box, perpendicular to the ramp. So we find this out because the sum of angles in a triangle equals 90 degrees or equals 180 degrees. So theta plus 90 degrees plus unknown equals 180 degrees. So unknown, the unknown angle is equal to 90 degrees minus theta. So if that's the case, then there is also a right angle here between the ramp and the perpendicular. And if that's the case, then 90 degrees minus theta plus this angle here, this angle, have to equal 90 degrees. So 90 degrees minus theta plus some unknown angle equals 90 degrees. Therefore, the unknown angle has to be equal to theta. So, if you're skiing down a ramp, then F net, then we're going to define our X and Y axes as X going up the hill and Y going perpendicular to the hill. And then this is normal force because I didn't bother to label it before. So F net X is going to be m times all of the acceleration that you're going to find, because you can't bounce up and down the hill, or you can, but that's going to be a very short acceleration. So perpendicular to the hill is going to be no movement. So all of the acceleration is going to be along the hill, is equal to ma is equal to negative mg sine of theta instead of cosine of theta, because this angle is because angle is with respect to negative y axis, not the positive x axis. Okay? So if that's the case, then f net x equals negative mg sine theta, which means that a equals negative g sine theta, which means that the acceleration is occurring in the opposite direction of the x-axis, which means that acceleration is downhill, which is what we expect to happen. And then f net y is equal to 0 is equal to MA is equal to 0 is equal to normal force minus mg cosine theta, again because it's respect to the negative y-axis, not the x-axis. So normal force is equal to mg cosine theta. So that's the equations for how you find the normal force and the acceleration accelerating down a ramp, or the force due to gravity pulling down a ramp. So this is pretty much all of the problems I have planned for today, but I'm just going to define three more forces that we use. Tension, T, is a force along the long direction of a rope or cord. So when you're being pulled on a sleigh by sleigh dogs, then you're being pulled by tension pulling on the cord, uh, being pulled by the sleigh dogs. And then there's also friction. We brought these equations up. We brought these forces up already, but friction of F is an opposing force, which means that acts in the opposite direction of acceleration or other forces, which slows or stops an object moving along a rough surface. And finally, we have a spring force, which is a force that follows Hooke's law. Force is equal to negative k times the displacement, where the farther, if you have a spring that is naturally this far out, then if you push it forward a little bit, so that's only this far out, then the force is going to be pushing this way by uh, by a magnitude of k delta x1. And if you have another force, and if you pull the spring out farther, then it's going to have a restoring force F equals negative k delta x2 pointing this way. So basically what the restoring force does is always tries to bring it towards uh, the initial position. So if you're farther out to the right, then it will move to the left, and if you're farther out to the left, it will move to the right. And this is an extremely important force that we're going to get into with further lectures. Uh, I hope that you all this was a good experience for you and like you learned a lot. If you have any notes for me, just feel free to send them to me. I'm not going to take it personally or anything. I'm just trying to learn to be the best lecturer that I can over Zoom. So, uh, thank you very much. I'll see you all on Monday. And I need to figure out how to stop this recording. Stop recording. There we go.